So hi, I think most of the people know me. So I'm Garima, and today I will be talking about things I did during my PhD, and I will be summarizing some of the things that I've done. And it is very obvious that I will be talking about the things that I did in my PhD with the title that is supposed to be my thesis title as well. So today I would actually be concentrating on the H1 halo mass scaling relation, looking at the physical processes that are causing or that affect the H1 halo mass scaling relation, and also trying to see how it's observed and how different kinds of observational techniques would make a difference in the inferred H1-HM relation. Yes, I would be calling H1 halo mass scaling relation as H1-HM relation because it's easier for me to say, but in case if I forget. So yes, this is what I'll be talking about. I would be summarizing a lot of things. So in case if I'm going way too fast, please feel free to stop me as well. And if I'm going over time, I might just skip over some things as well. So moving forward, why am I really interested in scaling relations? Scaling relation over here is definitely not the H1-HM scaling relation. This is the stellar mass halo mass scaling relation that has been around for a very long time. As we can see from the scaling relation, we are very much interested in it because we used to test the robustness of our simulations by testing out how well we can reproduce the scaling relations. Plus, scaling relation gave us a good idea about the physical properties of the galaxies and how they're affecting the overall properties of the galaxies, I guess. So first of all, if we look at the stellar mass halo mass scaling relation that I'm showing over here, it is a tight relation, tight being as compared to the H1-HM relation that I'll be talking about in a bit. It's a fundamental scaling relation, which is employed by various simulations to test their robustness. And we know that this is very consistent between simulations, which use very varied different physical prescriptions in order to define how the galaxies are forming or different physical processes that are being used in the simulations. So moving forward, why am I interested in the H1-HM scaling relation? The stars make about, from this baryon budget diagram, the stars make about 7% of the total baryon budget that we see over here, and gas or neutral gas makes about 2% of the scaling relation, of the baryon budget. So in order to understand more about the physical processes that go inside a galaxy, it seems like a good idea to venture into the regime of the H1 or H1 observation that we normally see. Because currently with ASCAP and all the other telescopes that are coming up, we would be observing the sky in H1 wavelengths at an unprecedented level. So what would we expect to see when we're looking at something with or how do we compare the H1 halo scaling relation with the stellar mass halo mass scaling relation? First of all, there is a huge difference between both of them. And the first difference that comes between them is the scatter. The H1 halo scaling relation has a huge scatter that could be seen from the observations of the alpha-alpha observation that I have plotted over here. This is a very straightforward diagram in which I'm just looking at the H1 mass of galaxies and comparing them against the velocity width of the H1 emission lines that we normally see. And what we find is that for every bin, which these velocity bins could also be kind of representative of the halo mass, is a huge scatter that goes about almost to 3 decks. But as we all love scatter because physics lies in these scatters, we are more interested in to see how we can constrain the scatter and what is actually causing the scatter that is going around. So during my PhD, I have mostly worked with semi-analytic models. And in my PhD, I have worked with Shark semi-analytic model, which is like an in-house ICRAR semi-analytic model. So SAMs in a nutshell use a dark matter only simulation. In my case, I've used SURFs and I've used 2 resolution boxes. One, that is a high resolution small volume box, and 2, that is a medium resolution larger volume box. Then we identify the halos using Velociraptor and tracked the merger trees using TreeFrog. And once we've identified these merger trees and come up with it, we populate these halos with galaxies using Shark and various numerical schemes that are defined in Shark. So all in all, we come up with a synthetic sky. And that also gives us an idea as to how much H1 would be there in the galaxies which if we track back to halos, we can also understand how much H1 would be there in our simulation in a particular halo. So once we have the H1 ready, the next part is to make comparisons with the H1 halo scaling relation that you get from observations, and to see how good are we doing if we just look at the out of the box H1 halo mass relation that we get from SHARC and compare that with the available observations. So on the plot, yes, on the plot on the left, what I show is the line over here, that is the H1 halo scaling or the H1 HM relation that we get from SHARC out of the box, the average H1 HM relation. On the panel, bottom panel, I hate words. On the bottom panel, what we find is that what I am doing is that the same average H1 HM relation, but now looking at the contribution from centrals and the contribution from satellites for SHARC. The maroon points over here are the H1 stacking, H1 stacking relation estimates from Guo's 2020 paper. I would be explaining way more about that in a couple of slides. This is just to give an introduction as to what we consider H1 halo scaling relation and how we are comparing it with different observations at this point. And in the bottom panel too, we do the same with comparing them with central contributions and satellite contributions of as measured by the H1 stacking experiment that was done by Guo in the 2020 paper. The green points over there are the H1 clustering measurements of the very same that were presented in Noble-Jones 2019 paper. But this is just to give an idea how we are doing. What we find is that we are agreeing well with the H1 stacking measurements till 10 to the 12, after which we start disagreeing a bit and diverging slightly. Same we can see in the centrals and the satellites observations, where centrals seem to agree to 10 to the 12, but then start diverging again, and the satellites start agreeing from 10 to the 30. But this is from observations point of view. On the right side over here, I'm comparing how it works or how different simulations, H1 HM relation, compare against each other. All of these simulations are giving very reasonable and almost identical, not almost identical, but very close stellar mass halo mass relations. They have passed the stellar mass halo mass robustness test, but they all employ different prescriptions for the physical processes. And what we find is that if we just look at their pure H1 HM relation, they are very different from each other. So this makes us curious to understand or to isolate which physical processes are actually playing the major role in determining both the shape and the scatter that goes around the H1 HM relation, so that we can understand how this could evolve with redshift. So during our investigations, what we found was that AGN feedback is the major contributor to the H1 halo scaling relations shape as well as scatter. So as we go from no feedback to stronger feedback, we find that with no feedback, you do not see any dip coming up. We just see a monotonically increasing H1 halo scaling relation. But as we increase the AGN feedback, we find that the dip starts becoming more prominent and starts earlier on in the halo mass regime. When we look at the scatter of the same, which I can show in the plot on the right, over here, the scatter is colored according to the black hole to central stellar mass ratio, because that's somewhat of an easier way for me to plot it. But one thing that actually jumps out of this is that as soon as we enter into regime where black hole masses or AGN is becoming a larger and has more prominent, we find that the scatter blows up. So from about 2 decks at the lowest halo mass limits, it goes out to almost 4 decks from 10 to the 12. And this is where this is also where we see the dip in the stellar mass halo mass relation as well, when we are comparing, or the change from going from stellar feedback towards the AGN feedback. And after that dip, it starts moving again. It starts increasing again. So we find that the AGN feedback plays a vital role in both making the shape or defining the shape of the relation, along with defining how much scatter would be there or contributing majorly to the scatter that is around the H1 halo scaling relation. Now, we know that AGN feedback is making a difference. What we were more curious about was to see if we could constrain the scatter that is around the H1 halo scaling relation using only halo properties, which would also help us come up with a numerical model that could populate halos based on just the halo properties with H1, just to have an idea if this is possible or not. And what we find is that we can constrain the H1 halo scaling relations scatter around that relation using the spin parameter of the halo, which is really a great constraint for lower mass halos. As we can see that it's really nicely correlated with higher the spin parameter, more the H1, lower the spin parameter of the halo, lesser the H1 in that particular halo. As for the higher halo masses from 10 to the 13 onwards, what we find is that if we get the fraction of the subhalo mass to the total halo mass, it is a nice indicator or helps constrain the scatter for the higher mass end as for the halo masses. As for the 10 to the 12 to 10 to the 13 halo mass regime, which we call transition region, but I personally like to call a very frustrating region, is there where the AGN feedback is at its peak and where the scatter is at its maximum. We can define the scatter using a combination of both spin parameter, because it still is a bit relevant in the 10 to the 13-ish region, and using the satellite to halo mass fraction. And combination of both can be used to define the H1 halo the scatter at this point. So using all of these values that all of these investigations and properties that we realized, we were able to come up with a numerical model which can populate halos based on their spin parameter, the fraction of the subhalo to host halo mass, and it could populate halos from redshift 0 to redshift 2. So we have come up with this model and it looks like it's great. What we found during our investigations for this is that H1 halo mass relation is complex. AGN plays a vital role in determining both shape and scatter, and the scatter can be constrained using spin parameter and fraction of the mass. Now, what we wanted to do next was to see what we found, as had shown earlier, that there was a discrepancy between the observed H1 halo relation. And when we compared that observed H1 HM relation with the predicted H1 HM relation, there is a discrepancy. And that led for us to understand, like, is it like some problem with the model itself, or is it to do with something else, maybe observational biases? So that's where our next steps come in. So we thought of doing H1 stacking experiments to try to reconcile the observed and the predicted H1 HM relation, and to understand. In order to do that, we wanted to reproduce the observed H1 HM relation using SHORC. We wanted to isolate factors that are causing the present discrepancy. And finally, we wanted to also compare different H1 stacking methods to understand which one are better at recovering the underlying H1 HM relation. So back to the plot that I had shown a bit earlier in the presentation. Over here, I'm going into a bit more detail. So as I told before, till 10 to the 12, we seem to agree well with the H1 stacking values. We go a bit further, and then we start finding discrepancy. Now, the points over here are from Gore's 2020 paper. The way they had done their stacking was they had used the group catalog from SDSS and the alpha H1 observations and stacked those values in order to get the H1 mass associated to a certain halo. We wanted to do an apples to apples comparison. So we went with making a mock survey for ourselves and repeat the entire process the way Gore 2020 would have done, or the other H1 stacking techniques would have taken into account, which I'll be going into in the next few slides. So for our mock survey, we made a light cone of the area of alpha alpha because it's huge and we would get better statistics, and it goes to redshift of 0.075. We put a magnitude limit on that mock survey, and we chose it to be gamma's magnitude limit because the other H1 stacking technique observations that we're looking at is based on gamma survey. So it was better to have a deeper survey at this point. Then we ran a group finder on the mock survey in order to get the galaxy groups in a similar way as it would be done for a survey of this scale, or for a survey like SDSS or Gamma would have done. And then we wanted to do our stacking. Now, I had said that we were going to compare different H1 stacking techniques, And we named these different H1 stacking. So this is where I'm going to explain what different stacking techniques we were looking at. So first stacking technique I'm going to explain is group stacking, is the one that has been used by Google in their 2020 paper. So for their H1 stacking technique, what they did was they identified the groups using SDSS catalog, they determined the halo mass, and using that they determined the virial radius of that particular group. They used that as their projected aperture, and then within a velocity window, they stacked all the galaxies that came inside that aperture in order to get the halo mass, H1 mass of that group, which is residing in a particular mass halo. What are the pros of this? Well, there are many non-detections that would be, or the many galaxies that would be lying above the magnitude limit of SDSS, which would be then captured and we could get their H1 masses. Cons, there might be some interlopers hanging around, which might be giving us some extra H1 mass in for those halos. So when I was comparing the H1 stacking technique for Guo's 2020 paper, we limited our group sample or galaxy group sample to galaxies which match the magnitude limit of SDSS to make it closer to the stacking technique that was used by the Guo 2020 paper. And once we did this and we did the mock H1 stacking as well, trying to see how close to the observations we come, what we find is that once we do that, we are very close to the observed results. So the crosses over here are the observed results of Guo 2020 paper. We trying to see different variations. We did 2 stacking windows. So one was around 700 kilometer per second and the other stacking window was 350 kilometer per second, just to see how big of a difference it's making. The maroon faded line here is the one that we get from the shark ref, or the intrinsic H1-HM relation that we get from shark. So as you can see from here, once we employ the mock stacking techniques, we are really close to the observed results. And we can recover the shape and also the observations. So this is the first stacking technique. The second stacking technique that we look at is what I call individual stacking. This is used by RE in their upcoming paper, in which they use a group catalog from Gamma, which goes to a band magnitude of 19.5, and they use Dingo for their H1 stacking observations. So what is the difference between group and the individual stacking? Well, in individual stacking, what they do is that they identify the galaxies that are associated to a certain group according to Gamma, and then they individually stack all of them together, and then find the mean, and then associate the mean H1 to the halo mass of those galaxies. So rather than using an entire aperture, they are individually stacking them and then adding them together to get the total H1 mass associated to that halo. Pros, you do not get interlopers coming in because they wouldn't be identified as part of the group. Cons, you would be missing out the non-detections that would be lying above the magnitude limit of the Gamma survey. But in any case, we did employ this stacking technique and then try to compare our results, or our mock H1 stacking results, with the observed results that RE in their paper were getting or are about to get. I think it's in preps, it's more like a future thing. What we find is, again, that we are able to reproduce results that are closer to the observations and in both shape and same observed quantities. And we are able to reproduce those results. But one thing that actually made us more intrigued about this entire process was that no matter how much changes we made to the stacking procedures, for example, in the group stacking, if we change the velocity width of stacking window, or if we change the aperture that we're looking at, and in this case as well, if we change the velocity width or velocity window, or slightly altering the apertures that we're looking at, it would change the lines to go slightly above or below, but it doesn't change the shape. We are losing the intrinsic shape that is behind that. And we would want to recover the shape because we know for sure that this is the shape that is there, because our entire mock is based on shark, which has this underlying H1HM shape. So we went into thinking, why is it that we are losing or we are washing out this feature of the H1-HM relation, and why we are not able to recover the actual shape or the underlying shape that we've seen over here? So what is the cause of this discrepancy? Well, we isolate three factors, or we think there are three factors that could be causing it. First, group finding. Maybe we are not able to find all the groups, or maybe we are a bit lacking on that aspect. Maybe it's the mass estimation of these groups that we are making is making a bit of a difference in the H1 halo scale or the shape of the H1 halo scaling relation. And finally, is it contamination from other sources that are somehow peeking in and changing the shape that we're normally seeing over here? In order to see how well we are recovering all the group, what we did was we did a small exercise. So from all the groups identified, we selected the central, or all the groups identified and their centrals identified. We tracked those centrals down to our simulations. And then for those centrals, we calculated the H1 that is around those centrals in a sphere of about 1 viral radius to 2 viral radius, just to see what we're getting or what we're getting for the H1-HM relation. And that is what I'm showing in the plot over here. What becomes evident is that we are able to recover, like though there is some differences in the amount of H1 that is recovered for every halo, the intrinsic shape still remains there. So it's not the group finding that is changing the shape shape of the H1-HM relation that we're finding in observations and the predicted one that we find in shark. The next point that we wanted to check was the halo mass estimate. So now what we do is we do the same exercise, but this time we use our viral radius that we're using is based more on the mass of, or the mass estimated for those groups, and along with plotting the mass of those groups. So the viral mass over here would be the one that would be estimated for those groups using different techniques. In this case, we are looking at mostly two halo mass estimate techniques. First is abundance matching, which relies on the luminosity halo mass relation in order to get the halo mass of the groups. And second is dynamical mass, which relies on the physical properties such as velocity dispersion and the radius of the fourth group to estimate the halo mass. And we again track down the centrals to the simulations, and then we use the viral radius that's based on the mass as estimated by abundance matching and dynamical massing, and trying to see what the H1 mass comes up next. And it becomes very clear that switching from the intrinsic viral masses to the abundance matched and dynamical mass estimates, it washes away the intrinsic shape of the H1-HM relation that we find over here. So as soon as we switch to the abundance matching, we find a monotonically increasing H1-HM relation. When we switch to dynamical mass, we find a more constant for some time, but then increasing H1-HM relation. So halo mass estimates seems to be the major player in determining the shape of the H1-HM relation. So if we determine them correctly, then we might be coming closer to the intrinsic relation. So the next point was, how well are we recovering the halo masses from either abundance matching or dynamical mass when we compare it with the actual viral masses of those groups? So in the plot here, I'm showing on the y-axis, we have the viral mass that we estimate using abundance matching technique, and then compare it for the intrinsic viral masses of those halos in shark. And from abundance matching, we find that even though they are close to 1:1 line over here, we find a huge scatter in the halo mass estimates. I have partitioned these groups in two groups, in which one group has galaxies at least 5 or less, and the other one has more than 5. And that's simply because if a group happens to have more galaxies in it, you are better able to estimate the halo masses and the other properties of it. When we do the same thing with the dynamical mass estimates over here, we find again a very large scatter for galaxy groups with less than 5 galaxies in it. But as we move towards higher membered groups, I would say, we find that the scatter is tighter as compared to the abundance matching technique. So both have their pros and cons, but yes, it seems like the way the halo mass is estimated is playing a very, very huge role in determining the shape of the H1 halo mass scaling relation that we normally see. Finally, looking at the contamination, we also want to determine how much of a big part contamination plays in the determination of the H1 halo mass relation. For that, over here, I'm showing a comparison. When I say intrinsic, what I mean by intrinsic H1-HM relation that I'm showing over here, this is for all the groups with at least 5 or more galaxies in them, because dynamical mass seems to be, because those are more reliable halo, they have more reliable halo masses assigned to them because of, it's just more reliable and it's easier to match up with them. So when I say intrinsic, I mean all the galaxy groups which have at least 5 or more galaxies that are above the magnitude limit, are under the magnitude limit of SDSS in this case. The points over here are the H1 mass measurements of the galaxy groups with 5 or more galaxies in them as measured by Go in the 2020 paper. Next line is what I call the best match halo. By best match halo, I mean the best match counterpart of the galaxy groups in our simulations. And the H1 mass that I'm comparing or calculating over here is the entire H1 mass associated with those halos. So this would be what the best counterparts of the galaxy groups in our mock survey are in the simulation, so that we can see how it is. And finally, the black points over here are the H1 stacking of those best match halo groups according to the 700 velocity width and the apertures of the halos as calculated by Gu in the 2020 paper. What comes up is that when we're doing group stacking, we find that from 10 to the 12-ish, we find contamination playing a bigger role because the total H1 mass for those best match halos is, for example, at 12.5, lower than what is being measured when we do it in a stacking kind of a way. We do the same contamination test with individual stacking technique, which is, I'm showing on the left, right over here. Intrinsic, again, is all the halos with galaxies, at least 5 or more, below the gamma limit in this case, because that's when individual stacking is coming in. One thing that I'm showing over here is then you have the best match halos, the same as always. When I say gamma magnitude limit is just me testing how well or how much H1 mass can be measured from just looking at galaxies which lie below the gamma limit, and to see how big of a difference that makes. And just to understand if going deeper would make a huge difference to this, we also try to see what would happen if a survey with the magnitude limit of waves is also in place, and how much of a difference that's making. And if we see that, if we go to a deeper survey, first of all, if we use individual stacking, the contamination is at its bare minimum. And with deeper surveys, we can also get more H1 mass as compared to gamma. So in conclusion, H1 halo mass scaling relation is a complex relation, which is non-monotonic and has a large scatter associated with it, which is mainly caused by AGN feedback. The scatter can also be constrained using spin parameter and fraction of mass of satellites and host halo. The discrepancy that we see between the observed and predicted H1 halo mass scaling relation is a combination of group finding, halo mass estimation, and contamination of galaxies that are not part of the groups. And finally, different H1 stacking techniques provide different limits. I would say with group stacking, it provides an upper limit to the average H1 halo mass scaling relation, whereas with individual stacking, we get a lower limit. So both have their pros and cons, and we have to consider what are the things that are causing, or if we consider all these effects in while making the measurements, we would be able to come closer or maybe able to understand better what we are getting from the observations. I guess I might have done a smaller talk, but that should be all. Thank you.
Great, thanks a lot, Garima. That was fantastic. It's great seeing your new results. And yeah, that made such a difference. So has anyone got any questions for Garima?
I have a question, if that's okay.
Yeah.
Very nice results. I love this a lot. And I was just wondering, those observed halo masses, so presumably the relation to ascribe a halo mass to a group or a system of galaxies in the observations was calibrated originally against some simulations or models. So how do your results compare against those initial results? I'm guessing you've got a lot more scatter in yours. So does that tell us that we need to go back and recalibrate those initial relations or consider them differently?
So one reason why we were doing, so you mean the scatter that was shown over here, correct?
Yeah, that's just depressing to look at, but it's wonderful to know. I mean, you have to know this because we want to plot observations with halo mass on the x-axis to compare and understand what's going on. Yeah. So it's essential, yeah. Right?
Yeah. So one of the reasons why the scatter comes along is, yes, we are using different simulations because the relation with the SDSS was actually calibrated upon Eagle simulation. So it is very different. They would be using a different halo finder, and the way it is going, the halos are what do you call it? Defined in Shark, for example, where we use a different halo finder as well. This was just to say how big of a difference it makes. One thing that we had noted, because one of the reasons why the scatter is so huge is also related to misidentification of satellites and centrals. So one of the reasons why these come up to a lower halo mass is because the satellites in those halos are actually flagged as centrals, which causes them to have a bit of a different value. So it's not just the calibration, but it's also some or different way we are looking at or we're identifying these groups. One thing that actually works better, what I would say, is with dynamical mass. If you look at a higher galaxies with, groups with more number of galaxies, where you would be able to get a tighter relation, which will be closer to what you would be expecting from simulations. But I don't know how well we could be able to calibrate or go back and change them, because no matter which simulation we look at, it's going to be a different halo finder run on it. I don't know if I've answered it incorrectly, but
no, you have. I think, I mean, it's hard, right? And we have to, but it's important to quantify this when we interpret the results. So I think this is very nice. Thanks.
Next up, we've got a question from Anju.
Yeah, sorry, I was just thinking about this discrepancy, and as Ryan said, yes, this is scary. The question I had was about the things that you mentioned earlier, which is about the AGN feedback. You were saying that AGN feedback seems to determine the scatter and the shape of this. So the different simulation, they implement this AGN feedback quite differently, right? Yeah. So I don't know how it is implemented in Shark, but is there a specific mode, for example, thermal versus the kinetic mode? Which one is more dominant in determining the shape of this H1 halo mass scaling relation?
So in Shark, we are using Darren's model. So it's mostly radio mode, as far as I remember. And I think I'm just changing. When I was looking at the different AGN or AGN feedbacks, is literally scaling the AGN feedback by making it 10 times stronger or two times. So I wasn't exactly making comparisons between them, but just making the overall difference, just to see how big of a difference by just changing the factor into it makes a difference.
Okay, strength. You're just changing the strength.
Yeah.
Okay. Yeah. Okay. Thanks. No, but really interesting result, Garima. Thank you.
Thank you.
Are there any more questions? If you are, feel free to unmute or put your hand up. I'll double check on participants. Cool. It looks like, yeah, I think if anyone does have any more questions, I'm sure Green will be happy to answer emails or get in contact on Slack or the A3D channel. So I just wanted to, before we end, I just wanted to advertise our next talk. It will be on March 9th, and it'll be James Esdale from Swinburne. So yeah, I encourage you all to attend that. Thank you for attending this one, and thanks, Garima, for that great talk.
Thank you.